Okay, welcome back to the second last talk of the semester. Today we have Marina Kounkel. She's at University of Vanderbilt, working with K-band Stetson. And she received PhD from University of Michigan, and then moved on to Western Washington University. At that time, I actually met her through SDSS. She is the leader of SDSS Uploaded to YSO group and doing wonderful science with that. And her research area is a local star formation history in the Milky Way, and those are also binary stars, and especially 60 analysis of star formation. That's a fantastic work over there. And I'm really happy to have Marina back. And so Marina, the floor is yours.
Thank you for inviting me again. This is my third talk in 5 years, and this is the primary reason for me to keep updating my slides. So I will try to primarily focus on the stuff that I haven't shown to you before. So age is the most important property of a star. Unfortunately, however, it is quite difficult to measure for most stars. It's not something that we are really able to probe for more than 99% of the stars. But what if we were to try? How might we go about it? Well, if you have a population of stars where all the stars have formed at the same time, such as in a cluster or in a moving group, or however else you want to refer to it, then it becomes fairly straightforward to determine the age of the entire population through isochron fitting. And nowadays we live in the era of Gaia, which makes this technique particularly wonderful. I'm sure by now Gaia requires no introduction. It provides three-dimensional positions and plane of sky velocities for more than billions of stars. And when Gaia came out, it revolutionized astronomy literally overnight, and it has influenced pretty much every area of galactic astronomy, but where I think it played the most significant role in identifying these common population, because they are, all the stars will share very similar velocity. They're confined to a very narrow volume of space. So here's an example of Pleiades, a fairly trivial case where you can just select all of the stars by hand. Through applying sophisticated clustering algorithms, we have found thousands and thousands of new coeval populations. Every couple of months, yet another paper comes out identifying a couple of hundred additional previously unknown clusters or other populations. For example, here's an example of one. In red are the structures that have been previously known prior to Gaia, and in black are all of the new discoveries. And as you can see, initially very close in, it was fairly complete. On the outer edges, there are a whole new parameter space to be discovered. And here's an example of a work that we've been involved in, where in yellow are all of the previously known, classically known open clusters, and in blue are a number of different co-moving structures and populations that we have identified. In total, within 3 kiloparsecs, we've found more than 8,000 of these populations containing approximately 1 million stars. And they are everywhere, they are ubiquitous, they are unavoidable. People are practically breaking their limbs, tripping over them in Gaia data. And in fact, it reached a point where most people who use Gaia to hunt for these clusters don't really know what clusters are anymore. We no longer know the definition of what a cluster is. Because all of these populations, they are messy, they are unique, they have a wide range in terms of their structure, in terms of their morphology, in terms of their mass, number of stars, density, etc. So there's a wide variety of the range on the environments. But regardless of what you refer to them, clusters, populations, moving groups, etc., they are still co-moving. And therefore, it's possible to determine their ages through isochron fitting. Here, you can see an example of some of these some of the HR diagrams for these clusters, where you have still sizable pre-main sequence population in the red, but eventually as they age, they drop down to the main sequence. And then after around 100 million years old in green, high mass stars start to die off in increasingly larger rate, and you start to develop a very clean turnout. So with this, we are able to determine ages for more than 1 million stars, which is quite a substantial amount. Problem is, so it's not enough. There are billions of stars out there, and so just 1 million is just a drop in the bucket. The population that are easiest to recover through clustering are those that are the youngest, because they still haven't really dispersed too far out from where they originally formed. All the stars still have more or less the same velocity. They haven't really evolved that much in their velocity dispersion. But as they age, most of these populations relax into the galaxy. They dissolve, shedding stars along the way. For example, here you can see a simulation of a cluster with, you might have a core, but most of the stars are being ejected every which way. And after you orbit around the galaxy once, well, if you assume that you had a uniform star forming history where at every single age you're forming approximately the same number of stars, you only have a handful of populations still left over. And the ones that are recovered at these ages, you only see the densest parts of them. Most of the extended and complex structure that once was associated with them has been gone. All the stars are somewhere out there, but we cannot recover them through clustering. They become incoherent. And that's a lot of stars to miss. So we need to do something different. And in fact, even the youngest clusters aren't really free from this. Some stars are very eager to leave their nests, and some do it much more violently than others. For example, here's a couple of stars that have been ejected outwards from the Orion Nebula, which is a very young cluster with an age of just a few million years. And these stars have been ejected through dynamical interactions, traveling with the speeds of several tenths of kilometers per second. And you can't really recover these stars through clustering anymore, because by definition, they are no longer sharing the same velocity as their parent cluster. So how might we fill this gap? Well, Gaia has gave us another gift. We are able to construct very accurate HR diagrams. And as long as we restrict ourselves to just this very narrow parameter space of the low mass young stars with ages, let's say, younger than 50 million years, carefully avoiding the main sequence, the binary sequence, all those pesky and horrible red giants, we can perform a relatively clean selection of the pre-main sequence stars. And what's nice about it is that we don't need to rely on the kinematics of stars to determine their membership, to estimate their ages. We can estimate the ages for these stars just from photometry alone, based on their elevation above the main sequence. Some contamination is inevitable. As they age, they get closer and closer to the main sequence. So eventually you start getting more contamination from the binary sequence, for example. But there's some trade-off between how clean of a sample you want to make versus how old of an ages you want to push it towards how comprehensive you want to make it. And just by comparing the young solar neighborhoods that we recover from clustering versus the one that we identify from selecting the pre-main sequence stars, you can see just how rich of a structure is present here that we're completely missing when we're just looking at the populations that still remain coherent for us to identify through clustering. And we can go on a tour of the solar neighborhood, slicing it into various age bands. For example, here's everything up to 2 million years. We have Orion, molecular clouds, Ophiuchus, Perseus, Taurus. I trust that most of you will appreciate that this is pretty much all we knew about star formation going back approximately a decade ago. That's all of these notable nearby star forming regions. Here is 2 to 5 million years. We're starting to fill some of these regions, starting to probe some of the more distant regions as well. 5 to 10 million years, starting to get Vela OB2, which really starting to become quite a popular star forming region in the last decade or so. 10 to 16 million years, starting to get the older parts of SCO-SEM. 16 to 25 million years. And finally, at the ages older than 25 million years, we are reaching terra incognita, because these stars, they are too old to have been on radar of the star formation community. But we didn't really have any methods of identifying them prior to Gaia, but they're also too dispersed to have been on the radar of people who have studied open clusters. So this is an extremely exciting era where we can actually disentangle all these various layers by age. However, after you reach the age of around 50 million years, you kind of hit a wall. As you get closer and closer to the binary sequence, the contamination is just going to swarm you, and you aren't really going to recover any meaningful information at ages older than that by making a selection on the HR diagram. So we need, in order to push it further than that, we need to have some other method that would enable us to probe the age of older stars and the more massive stars such as solar type stars. And there are a couple of things that we can try. Magnetic activity is a strong indicator of age. Young stars start out fully convective. Convection generates dynamos in a star that creates strong magnetic field. And magnetic field precipitously decreases over time. Magnetic field is not something that is easy to measure directly, but it impacts many aspects of a star. For example, through magnetic fields, you are forming spots on the star's surface. And here is a diagram showing temperature versus age of a star color-coded by what fraction of their photosphere is covered by spots as an average in each two-dimensional bin. And as you can see, at the youngest end, when you still are fully convective, when you're still moving along the Hayashi track, you have very large spot coverage, and the stars that remain fully convective tend to stay pretty strongly magnetically active throughout their lives. As soon as you start developing a radiative core, your magnetic activity starts decreasing, and these stars over here would have a very small radiative core. These stars would be almost completely radiative. And then after you reach the main sequence, the spot size continues to precipitously decrease over time. Our sun is a fairly evolved star, kind of found at the left topmost corner of this plot. It has a fairly wimpy star spots. On the other hand, young stars can have star spots with spot sizes in excess of 50% of the stellar surface. You can't really judge the spot coverage on the star by star basis. There is a lot of range at a given age, especially on the given orientation of a star. But this diagram is just an average of many thousands of stars. But magnetic activity also influences stars in other ways. For example, if a star is rotating around its axis with a particular speed, magnetic fields slow the rotation down by dragging the star back. So initially, at the youngest ages, stars tend to rotate fairly fast. As they age, the rotational periods precipitously slow down. This has been this technique is known as gyrochronology. That is to say, if you are able to estimate the rotational period of a star, you should be able to infer its age. Gyrochronology is nothing new. It has been known for a while, since the 60s, as most things are. And there have been some seminal papers on this topic back in the early 2000s. But it unfortunately didn't really go anywhere much, because although in principle it's a simple concept, in practice you just need to have a lot of data in order to measure these rotational periods. How might you be able to do that? Well, just to take a light curve of a star. I'm sure you've seen a lot of very similar plots looking at exoplanets or eclipsing binary stars. It's just same principle, only slightly different shape of the light curve, because the spot is slightly cooler than the photosphere of a star. When a spot is facing us, the star is going to be dimmer. When a spot is facing away from us, a star is going to be brighter. So by observing a complete period of star being dim to bright dim again, we are able to infer the rotational periods of a star. Now, it's a bit more complex than that, because you could have multiple spots that might interfere with one another, and if spot is found on the equator, then that would have a slightly different period than a spot found higher up due to the differential rotation of a star. But still, these complexities are a bit too messy for us to get into. But in order to generate a light curve, you need to have a lot of data. You need to monitor the star repeatedly over a prolonged period of time. And ideally, you need to have fairly good precision in your photometry, because these spots, they don't really induce variability more than a couple of percent at most, and usually much less than that, depending on the radiation of the star, depending on its age. So it's not really something that was easy for us to do prior to Kepler. With Kepler, there have been a number of clusters that have been observed by it, and people have meticulously analyzed each and every light curves of these stars associated with these clusters to carefully measure rotational periods that are not biased by any aliasing, that don't really have any systematic effects, that as clean of a periods as you can possibly get. Here you can see Pleiades, here you can see some of the older clusters, and you can see a clear progression from shorter periods to longer periods as the stars ages. However, Kepler had a really limited field of view. And even if you add K2 mission, that didn't really expand its footprint significantly. It doesn't cover the entire sky. As such, we have only a handful of clusters that happen to fall inside the area that it has covered. And so there's sort of gaps between these sequences for these clusters. So how might you be able to infer the ages of stars between them? Well, if you have photometry of the stars, you can infer their ages using isochrons. But if you've used isochrons, especially for the premium sequence stars, you probably know that it's easier said than done. There are some irregularities that isochrons still don't really match the data perfectly. There are also theoretical gyrochrons out there, but they are even worse than the isochrons. For example, this one, it was calibrated to Praesepe, at least on the hotter end, but it may match some of the older clusters, but it doesn't match the younger clusters, and it completely gives up at the cooler temperatures. This one does a bit better, but also it's not really the most optimal. There's still a lot of uncertainty in these gyrochrons when we're trying to infer ages on the stars in the real data, because there's still a lot of physics that we don't really understand how the rotation is being influenced at each distinctive temperature. So we need to have much more data, either in order to construct empirical gyrochrons or in order for us to better calibrate these theoretical isochrones. And we can't really do that with Kepler. I mean, Kepler is no longer operational anymore. It can't really produce any more data. But nowadays, we have TESS. TESS has an advantage that it has a much larger field of view. Just in the single pointing, its area on the sky is 20 times larger than that of Kepler. It has a field of view of 96 by 24 degrees. And furthermore, TESS constantly looks at different portions of the sky. So it stares at one portion of the sky for a period of around 27 days. And then it goes to the next sector and it's able to cover almost the entire sky in as little as around 2 years. But there are no perfect things out there. TESS does have significantly lower resolution than Kepler does. A single pixel of TESS is only around 20 arc seconds, and you can fit a lot of stars in 20 arc seconds, especially in dense clusters. So contamination can be a bit of a concern. TESS also has lower sensitivity than Kepler. Let's say it can't really look at stars that are as faint as Kepler can. Still, you can still go pretty far out, down to around 16th magnitude, but still. And TESS is a wonderful instrument. We love it, but it has some issues. Let's put it that way. So TESS data comes in two different flavors. There are target pixel data, where you have small cutouts of individual stars. These stars were chosen as most likely objects to host planets. That is to say, they are some of the brightest stars. They are found in the regions of lower contamination from the nearby sources, so generally avoiding the galactic plane. They have some additional restrictions on the spectral type. And it adds up to only a few tens of thousands stars in total. But these stars have been observed with 2-minute cadence, and the light curves for them have been processed and are readily available. Chances are, if you're reading a paper that's utilizing TESS data, most times it would use target pixel data because it's just the most accessible. There are also full frame images. So the entire footprint of TESS that it's observing at a given time, it's recording this entire 24 by 96 degree field with a cadence of around 30 minutes for the first 2 years. Then it has increased the cadence down to currently of around 2 minutes, I think, as well. The problem is that these full frame images contain a lot of stars, and it is very computationally intensive to generate light curves for all of them. So they haven't been pre-processed. There are tools out there that will help you generate light curves from these full frame images, but it still takes some time to generate light curves for even a few thousands of stars. But depending on which method you use to generate the light curve, you might get very different light curve shape, because TESS has a lot of systematics. So a single sector of TESS, a single pointing, spans around 27 days. During this time, TESS orbits around the Earth 2 times. So it has an orbital period of around 13 days. And you can clearly see the divide between one orbit and another in the raw data. For example, here you have a very strong disconnect in the flux between one orbit and the other. In the other orbit, you also have a disconnect here. Here you have 2 different artificial trends. Here you have the same long period trend that's also not real, that's also artificial. Here you have some spikes at the beginning or at the end of each orbit. So you need to get rid of these systematic trends somehow. The easiest way to get rid of them is through fitting a polynomial to a light curve. But by doing that, well, if you're just looking for eclipsing binaries or planets, it shouldn't really affect you all that much. You're still going to have eclipse just as you were before. But if you're to looking at the longer period rotational variability, then it's kind of hard to differentiate between the real intrinsic variability and the systematics of the instrument. So if you were to fit a polynomial, here are the corrected light curves. For the shorter period systems, you still are able to recover their period just as well as you were before, actually better even, because you're not really affected by this long-term trend. But the longer period rotation has been completely, you no longer see as clean a rotation curve as you did before. You have injected an artificial period of around 7 days. So there are a lot of complexities in how you can correct these light curves, but in practice, it's very difficult to go to the periods longer than 13 days, and in practice, longer than 7 days in most cases, because of these systematics. And that's a bit unfortunate because there are a lot of stars that have rotational periods much longer than 13 days. Still, when people generally generate these light curves, it's not uncommon to have a small army of students who would look through each and every one of these light curves to ensure that you have as accurate of a period as possible, that you don't have any of these systematics, that the light is originating from the exact stars that you have and not from a star that is neighboring to it still in the same pixel. But we have a lot of data of the stars with known ages. There are thousands and thousands and thousands of them. And that started to become a bit too unwieldy to actually go through them one by one. So after some point, it's better to trust just to trust your data, to hope that there is going to be a strong enough signal that will beat out all these systematics. That is to say, you take the data quantity over data quality. And by generating light curves for hundreds of thousands of stars, we do have quite a strong signal. So here is a plot of temperature versus dominant period of various stars, color-coded by their age. And there are a lot of different features in this diagram, so let's go through them one by one. So the first thing I wanted to focus on is this gap right over here. So there are a lot of stars on this side of the diagram, there's a lot of sides, some stars on this side of the diagrams, but nothing really in this gap. It's corresponds to temperature of around 7,000 Kelvin, and that is roughly where the craft break is. What craft break is that it separates the stars with those that have convective envelopes and those stars that have radiative envelopes. In order to have star spots, in order to see rotation, you need to have convection. So most likely the stars on this side of the diagram are rotational variables. On the other hand, on this side of the diagram, you no longer are able to be sensitive to rotation, but there are a number of instability strips among the more massive stars. For example, here are just the location of some of these pulsating variables that we see here, slowly pulsating B-type stars, Gamma Dor and Delta Scuti particularly are quite obvious in the sample. I won't go into too much detail of the for these systems. They do show some interesting age trends as well. Apologies. But the most interesting one of which are the Delta Scuti stars, where we see a bimodal distribution of them, that we have a clear separation between the main sequence Delta Scuti stars and the subgiant Delta Scuti stars having a longer period. Now, normally, if you're to just go out to your favorite catalog of variable stars and download them and look at all the Delta Scuti stars, you'll see a continuous period distribution up to a period of around 7 hours. Here, so we do have this bimodal distribution. And most likely, this originates from the fact that we have an age-limited sample. We don't really have any stars here with ages older than 1 billion years. And pulsating variables tend to have a period luminosity relationship with the brighter stars having longer pulsation period. So these subgiants, they are counterparts to much more massive main sequence stars than the main sequence stars that are currently on the instability strip. So they are much more luminous, therefore they have a longer period. And as you start allowing more and more evolved stars, you eventually will fill in this gap. But again, I won't go too much into it. So let's go back to these rotational variables. Here we see a very clear gradient in periods going from the youngest ages having fairly fast periods to the older ages having fairly slow periods. And this is very similar to what we've seen before with Kepler and with ground-based surveys, only because we have a much more continuous distribution of ages. We see just a smooth rainbow of stars without really any gaps there. We do eventually run into the limits at 7 days and 13 days. Again, quite unfortunate because there are, you can see how it would continue for the older stars, but that's all that we can work with right now with TESS. And this provides us with the tools to infer ages for stars that aren't necessarily part of the moving groups. Or at the very least, it would be if there wasn't a small wrinkle in here. There are also a lot of stars over here that have very short rotational periods. They're so-called fast or rapid rotators. Rapid rotators also spin down as they age. So initially, they might start with a period less than a day in a population of stars that have a typical period of 5 days. And if a population has a period of around 20 days, you might have fast rotators with a period of 5 days. That is to say, it can become quite difficult to distinguish between very old fast rotators and very young slow rotators. Eventually, they start overlapping. They can be quite difficult to separate if you don't know their age. Let's ignore the sprinkle for now. We'll come back to it later. Let's filter out all the fast rotators. And let's try to analyze the age trends in this plot. Except this parameter space may not necessarily be the most ideal for us to fit a polynomial to determine their age, because you have a lot of very odd curves in this graph, and eventually everything kind of turns around, and you're starting to have faster periods on the low mass stars as well. So it can be kind of hard to replicate all that with a polynomial. Thankfully, there is a much better parameter space that we can use that also depends on the period, but it also depends on the mass and the radius of the star. That is to say, if we were to look at the angular momentum of stars, which is a slightly more fundamental properties of a star than rotational period. And here, we're looking at temperature versus angular momentum, again, color-coded by age. And here you can see that all of these low mass stars, where before all the periods have been piled up on top of one another, here they are quite clearly, we can clearly separate them out because the angular momentum of a star is still going to decrease even if it doesn't really change its rotational period if it shrinks down. So the younger stars, the younger they are, the more angular momentum they're going to have, and it continuously drops down. And here on the high mass end as well, it's fairly fanned out. So we are able to fit a polynomial to this relationship. And if we do have a polynomial, we can take a derivative of it to see how fast the stars lose angular momentum as a function of age. And here is the derivative of angular momentum as a function of temperature. You see that not only do the youngest stars have the most angular momentum, they also lose their angular momentum the fastest. This black line shows the maximum at a given age range. The high mass stars are most effective at losing angular momentum. Low mass stars are a bit less efficient in this process. And because we do have this fit to all these relationships, if we have catalog of stars with known rotational periods, we can determine their ages without relying on either their kinematics or on their photometry. Unfortunately, TESS isn't quite there to provide rotational periods of all the stars across the entire sky. I'm hopeful that it's something that will be possible in the next decade. Therefore, it will be able to increase our sample of stars with known ages by an order of magnitude. But there are some known rotational periods of stars from Kepler, the main Kepler field, as well as the K2 fields. And the clusters that are present in these fields, such as Pleiades or Praesepe, we are able to recover their ages just from rotational periods alone. And for example, in the Kepler field, you see that most of the field stars that are not associated with the clusters, they are quite old. They might have some contamination from rapid rotators, but for the most part, we tried to clean it out. In future, gyrochronology can be an effective tool for us to see the age distribution of the stars in the solar neighborhood. Therefore, we'll be able to see the star forming history of the galaxy in as much detail as we couldn't have before. But there's still an issue of those pesky rapid rotators. What can we do about them? Why do some stars spin up? Which stars spin up? How do they do it? Well, the answer to that is actually surprisingly simple. If we're to isolate ourselves to just a narrow age range to reduce any of the smearing, and if we're to construct an HR diagram, we see that on the cluster sequence or on the main sequence at these ages, you primarily are dominated by the slow rotators. On the other hand, on the binary sequence, you have a lot of very fast rotators. Here we can see the same thing, that the main sequence peaks at much longer periods, and the binary sequence tends to have an excess of these rapid rotators. It's not exactly one-to-one. There's some cross-contamination. There are some slow rotators here. There are some fast rotators here. But it does seem to be quite apparent that there's something about multiplicity that is influencing the stars to speed up. And it might be tempting to think, well, maybe it's just tidal effects. If you have two stars very close together, then eventually the rotational period is going to match the orbital period. Except it doesn't quite work out, because here is the distribution of the period of separations for a binary for all binary stars. Most common separation that you would have is around 30 AU, or it would have a period of around 500 years. To create these rapid rotators to be tidally locked, you would be looking at just this tail end of the distribution. So there wouldn't be enough of these short period systems to account for the ubiquitous nature of these rapid rotators along the binary sequence. So you need to have a lot of unresolved binaries with longer separations. And in context, this plot was done with Gaia data. Here are Gaia would in single pixel in Gaia would cover separation of approximately 40 or 50 AU for the stars at these distances. And it can't really come from a very short period systems either, because if we look at the spectroscopic binaries that tend to have fairly short period of less than a few hundred days, the rapid rotators are less common among these spectroscopic binaries than they would be in the population at large. So we're specifically looking at the stars with separations of a few to few tenths of astronomical units. And so why do these binaries spin up? Well, we can take a look at their earliest stage of their formation. For example, in Orion, which has an age distribution from less than 1 million years to up to 10 million years. And if we're to separate the stars into those that still have disks and those that no longer have disks, we find that very few stars with disks have rotational periods less than 2 days. So there seem to be some sort of boundary at the period of 2 days. So we can define all the stars that are rotating faster than that as TESS rotators. On the other hand, as soon as these stars lose their disks, they happen to spin up. And if we were to look at their distribution as a function of age, looking at the fraction of stars with periods less than 2 days as a function of age, overall, if we were to take all of the stars in Orion, approximately a quarter of them are going to be rapid rotators, no matter which age spin you're looking at. But if we were to specifically look at the stars without disks, then rapid rotators tend to lose their disks the earliest. So almost half of them, half of the stars that would lose disks at these ages would be rapid rotators. And if we do assume that these stars are binaries, that kind of makes sense, because wide binaries tend to disperse their disks at faster rates than single stars do because of the dynamical interactions. Eventually, though, as more and more stars would lose their disks, regardless of the rotational speeds, this fraction is going to go towards the median. Among the classical auditory stars, the stars with disks, you see a different trend. At the youngest ages, very few of them have periods less than 2 days. But eventually, that fraction is going to increase over time, because although the disks are able to delay the onset of rapid rotation, they are not able to suppress it. So eventually, all these stars are going to accrete the excess angular momentum, and they're going to spin up. Why do these binaries have excess angular momentum? So it's not really something that we understand fully quite yet, but there have been some simulations that suggest that wide binaries are less effective at dissipating their angular momentum via outflows in the earliest stages of their lives. And by wide here means binary with separations of around 40 AU. So if they are less effective at dispersing angular momentum, they will have more angular momentum to start with when they lose their disks, and all that angular momentum is going to be accreted onto the stars, resulting in its spin-up. But this is all assuming that at these youngest ages, all the rapid rotators are still also binaries. And it can be a bit hard to test, because here at the older ages, we can still see that all of these rapid rotators are dominating the binary sequence. In the younger populations, we don't really have a cleanly defined binary sequence because we have a significant age spread and the fast evolution of these stars. Everything kind of piles on top of one another. It becomes hard to distinguish a star on the binary sequence that is older versus a younger star that is single. So we need to have some additional methods to confirm that even at these ages, these rapid rotators are binaries. One of the ways in which we can do it is to compare the distribution of some properties that doesn't depend on age. For example, inclination. Inclination can be measured from trying to measure radius of a star using two different ways. For example, if we know the period of a star and we have its rotational velocity from spectra, we are able to infer the radius of a star just using simple geometry. Rotational velocity is usually v sin I, so we have r sin I as well here. We can also estimate the radius just by estimating how big of a star needs to be of a given temperature at a given distance to produce a certain amount of light. So this is just a Stefan-Boltzmann relationship that will give us the radius. Combining these two terms together, we are able to infer the inclination angle. On its own, inclination angle is meaningless. Stars are oriented every which way. It's a property that doesn't depend on anything other than just random chance. It certainly doesn't depend on age. But this is only effective for the single stars, because if we have, for example, a binary, some of these assumptions begin to break down. For example, in a binary, you might be able to measure all these parameters well, but the flux you're going to have a contribution from 2 stars rather than just 1. So if your flux is going to be overestimated compared to a single star, then your sin I will become systematically underestimated. And we can look at the sin I distribution of slow and fast rotators. And we do indeed see that slow rotators tend to be found right over here. Most of them are appear to be adjoined just because of the how the measurements are made. But fast rotators tend to have systematically lower inclination angle distribution. So this will be consistent with them being unresolved binaries. Now, if we also compare double-length rheoscopic binaries, they tend to have very large sin I's. That's because for them, the V sin I isn't really accurate because it doesn't really measure the rotation of the individual stars, but it's rather broadened by the orbital velocity of the system. So here, these sin I's are also inaccurate because of the excess of V sin I. But here, these fast rotators, they are far enough apart that it doesn't really impact their V sin I, but their fluxes are overestimated. And if that's
Marina, can you? There's a chat. There are 2 questions. First, I'll read the first question first. But I think the second question first. So Cecilia asks, in the context of gyrochronology, like a schematic flow, all stars will converge to a single rotational period as a function of age that depends on the mass after 100 million years. Can you explain how these early conditions would make binaries escape this and end up rotating faster for so long?
It's the fast rotators are also spinning down, and they are also eventually they do kind of catch up to where the slow rotators are. I mean, not precisely, but they are also spinning down at a very similar rate as the slow rotators do. They are starting from much higher angular momentum to begin with than single stars.
Cecilia, does it answer you?
Yeah, well, I would expect that to happen in much faster timescales, 100 million years or so, but we can talk later.
Initially, there's just a wide range of distribution, and also maybe there's something to do with the spot location that I will get to in a couple of minutes.
Yeah, there was an older question about angular momentum from Christina. So could you please elaborate how you obtain the angular momentum from the rotational periods of the stars in your sample?
If we have rotational, the angular momentum depends on the period, on the mass, and on the radius. Mass and radius we can infer for stars based on their photometry. Of course, doing it from spectra would be a bit more reliable, but for the most stars, because most of the stars in the sample are going to use main sequence stars, just because we know how bright they are, we should know the mass and radius as well. And so by multiplying all these quantities together, we get the angular momentum. And that seems to just create a slightly more smooth distribution than the period alone.
Right, thank you.
We see here that even at these youngest ages, the rapid rotators tend to be unresolved binaries. And if that's not convincing enough, how about we actually resolve some of them? It's not something that we can do in Orion, but Taurus is a bit closer in at a distance of around 140 AU. It's a very notable star forming regions that people have studied in a lot of detail. There have been a lot of studies of high resolution imaging, and many of the stars in Taurus can be resolved down to 3 AU. So we also need to have rotational periods for these stars. So in total, these are all the stars for which we have high resolution imaging and for which we also have rotational periods. In the sample, there are 5 binaries that can be resolved. 4 of these binaries are rapid rotators. And all 4 of these binaries have the separation less than 30 or less than 40 AU. So exactly in the separation range where we think the stars should spin up. The sole result binary that isn't a rapid rotator has separation of approximately 150 AU, so that's probably too far out to have a meaningful effect. But while we are still looking at the inclinations, we can also examine a couple of other fun properties. For example, we can compare the Sinai distribution as a function of how strong the variability is in these young systems in Orion. And what we find is that the strongest variable stars tend to be most likely to be edge-on. And the more weakly variable stars tend to have more face-on inclinations. That kind of makes sense because if assume that you have stars of the same age and they have the exact same spot coverage. If you are edge-on, you are able to see a spot rotate in and out of the field of view fully, or at the very least, it will give you the greatest chance for the spot to have the greatest amplitude on the light curve. On the other hand, if you have an inclined system, then the spot, a portion of the spot will never rotate in or never rotate out of the field of view, and that will significantly reduce your variability strength. Similarly, we can also compare the stars with disks and stars without disks. What we find is that a lot of stars without disks tend to be edge-on, but the stars with disks tend to be biased against edge-on inclination. And that also makes sense because if you do have disk, your opacity is going to be much higher. And if you have a magnitude limited sample, like we have here, because we need to take spectra of all these stars to get their temperatures and V Sinai, you wouldn't necessarily be able to see these edge-on extinct systems with disks like you would be if they didn't have disks, or if you're looking at these systems face-on. But this there's a bit more to it than that. It's not necessarily an effect of the disk itself, but rather it's more of an age-dependent effect. Because if we were to look at the Sinai distribution, both for the stars with disks and the stars without disks, split up by age, we see the same bias against edge-on systems at the younger stars without disks as well. So chances are it's not the inner disk itself that provides opacity, but rather they're probably a puffy halo or outer debris disks that still remains behind for the first couple of millions of years, even if the inner disk is gone and you're no longer accreting. Eventually that disk will settle down and you'll be able to see these stars edge on without opacity. So we have a bias as a function of age in terms of the inclinations of the stars that we are able to see. And for the most part, it's probably going to be fine, except imagine the circumstances in which you have a preferential allocation for some of the spots. For example, in our sun, the spots are preferentially forming around the equator. In some of the young stars and some of the magnetically active M dwarfs or red giants, the spots have been preferentially found to be located around the poles. So if you're preferentially looking at the younger stars pole on, and the older stars will have a more equitable distribution with more stars being located edge on, then this would introduce a bias in your photometry that you might be tempted to attribute to age, but it's also due to the difference in the spot coverage. So it's just something to think about in the future as we investigate these effects further. But with this, I'll come to the end. So just to summarize, variable stars, particularly rotational variables, can help us understand a number of stellar properties as stars age. In particular, it allows us to measure, to estimate the ages of our stars using gyrochronology. It's not something that we are at the position to apply regardless of where the star is, but hopefully over the course of the next 10 years, TESS is going to come through and we should have all these rotational periods. And assuming that we are able to separate out all of these unresolved binaries from the sample, which is granted a big if, we should have the largest ever catalog of relatively precise ages. And that would allow us to study the star formation history of the galaxy in much more detail than we can today. Thank you.
Thank you, Marina. So, question to Marina. From here first. Okay. If you have a question, please raise your hand so that I can actually see from here.
I think there are a couple of more in the chat that I can.
Yeah. So one was asking your email. I think Cecilia has a more question probably. And David commented on here to go. But thanks for the great talk. Normally study isotopic abundances and their relation to stellar ages. I didn't really understand the process of gyrochronology based ages, but your talk cleared up much of its confusion and wanted to read more. So so I have a question actually. When you at the very beginning, you decide the age of clusters based on isochrons, and then one of the last slides you show that a lot of some of the edge-on young stars. So when you actually go to very young region, I often see a lot of young sources with this. They actually fall quite underluminous, so they will appear in your age pretty old. Is that correct?
Probably yes. I mean, it's isochrons aren't terribly precise, and there are a lot of factors that can influence a star. There are some stars out there that appear to be too bright for the isochrons for the spectral type, based on all the other indicators. So, and there are similarly some stars that may appear to be too dim, but it also, if photometry at one band may make a star appear to be too faint, maybe another band could bring it back up, and depending on the specific parameter space that you can use, you might infer different ages for these stars.
Yeah, so I think I found that about 10% of at least some of the clusters that I noticed, they fall below on the luminous regions. So they were, and not as so. Since there's no other question here yet, I have another question about the spot coverage in tomography relation. So young stars, these, as far as I know, they are like somewhat about around 50% coverage is possible, especially around the polar region.
Yeah, even greater than that. So there have been some systems with 70% spot coverage, which is at some point you have to wonder if we're just starting from a right temperature, if it's more correct to interpret it as spots or just the bright spots that are 30%. But yeah.
Yeah, so I was wondering, how does that affect, especially when you look at the edge-on, if it's like 50% or 70% coverage, edge-on or some inclination would appear basically the similar. Yeah.
Yeah, no, certainly if you're looking at the star pole on and you have a polar spot there, then you might you might think that there is a greater spot coverage than if you were to look at the star edge-on.
Okay, since it's 1 o'clock, I will. There are some people who will ask questions after you talk, but is there any other question? Then otherwise, we'll thank Marina. I'll see you next week. So Marina will stay here if you have more further questions, and I will stop recording right here.
Hey, Marina, this is Chad Bender, and I have a semantic question.